In this section of chapter 8, I would like to go over Lewis structures that show resonance and also Lewis structure that shows exceptions to octet rule. Let us draw a Lewis structure for ozone or O3. Each oxygen has 6 valence electrons or 6 outermost electrons, so 3 of them would have 6 times 3, 18 valence electrons. Now put one of these oxygen in the middle and two on as outer atoms, okay, and then give noble gas configuration or octet to the outer oxygen atoms. So that means 2, 4, 6. I'm adding 2, 4, 6. So that makes 8, 8, 16. Now we have 18 electrons altogether. So the remaining 2 electrons has to be placed on the central atom. Now the central atom oxygen has only 6 electrons, but we need to have 8 electrons. So what I'm going to do now, in order to make it 8, you can bring a pair of electrons from outer oxygen to in between. So it can happen like this, and that would give rise to this structure, which is shown right below the structure that I have just drawn. So in other words, having a double bond on the left hand side. I can also bring a pair of electrons from the rightmost oxygen to in between. That would give a double bond in a different location. So let me draw that too. So if I have oxygen, 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 and remember that I'm talking about giving 8 electron. So this would now remain 6, and then bringing a double bond here, 6, 8. So these two structures are not identical. The top structure, let's draw a line, that way it no. Let's call the top one structure 1, next one is structure 2. In structure 1, oxygen, oxygen on the left has a double bond. So it has to be a shorter distance between that double bonded oxygen. So this is going to be shorter. Let me write down that. Shorter. And single bonded oxygen would be longer. Similarly, in structure 2, the right hand side, double bonded oxygen would be shorter, and single bonded oxygen would be longer. So if you solely go by this structure, one of these structures, then we'll have to believe that two different bonds would have different lengths. One of the oxygen-oxygen bond would be shorter, and the other oxygen-oxygen bond would be longer. And let's see what experiment suggests. This shows experimental results. Now you can see that in ozone, oxygen-oxygen distance is the same. In other words, if this is one oxygen here, this is the other oxygen, this is the other oxygen, and there is no difference between these two lengths. Even the Lewis structure, as we have drawn in previous slide, has shown one with a double bond, which it should be shorter in length, and the other one single bond should be longer in length. So this appears to go against experimental finding that those two lengths are identical. And that's how scientists decided to consider resonance. That means whenever more than one possible structure, then actual structure would be given by the combination of all those possibilities. In other words, if ozone is made up of, let me show you, double bond, single bond, and the other one would have single bond, double bond. Here I'm not showing all the electrons. So actual structure would be given by the combination of these two. That means what appears to be double bond here, next time it becomes a single bond. So in other words, that double bond, second bond, is moving around between all these oxygen atoms, and that gives identical bond length. And this phenomenon is called resonance. And individual structure, Lewis structure, is called resonance structure. And combination of these resonance gives what is called resonance hybrid. So what we learned so far is a number of times you'd find this, that one Lewis structure cannot accurately depict a molecule like ozone. There are many other molecules like that where single Lewis structure cannot sufficiently explain all the bond lengths, bond strengths, angles of that molecule. So when there are multiple structures possible, we call them resonance structures to describe the whole molecule. And whole molecule would be given by combination of all those resonance structures. Now we are going to show you a structure of formate ion. It comes from formic acid, which is an organic acid, HCOOH. If you get rid of this hydrogen, you get HC double bond O, O minus. And that's what they're showing you. Now, when one structure is given to you, question is, can you find out whether there is any other resonance structure possible? And how can you do that? Let me show you that. Let's now focus on the structure. This is structure, say it's given, and you're supposed to find out any other possible way of writing resonance structure, another resonance structure. Now, resonance structure provides a pathway for electrons to go through. Now, you're not supposed to exceed total number of bonds. For example, around carbon it should be 4 bonds, so you cannot assign 5 bonds around carbon, so that would not be allowed. Secondly, you cannot break equivalent bond. In other words, say I have electron pair in between carbon and hydrogen, I cannot remove it from that, because that would mean having no electron pair between carbon and hydrogen means there is no bond. You're not allowed to break an equivalent bond. So only thing I can do, and can at least try doing, is bringing this pair of electron from oxygen to in between carbon and oxygen. That would temporarily give the carbon 5 bonds. So that means one of its bond has to be broken. So the double bond, one of the double bond, is going to dump its electron pair onto oxygen. And that's how you're going to get a structure number 2. So this is structure 1, and the other one is structure 2. In doing that, I haven't broken an equivalent bond. Only the double bond, the second bond, is broken from the right side, and that's quite all right. And these are 2 possible resonance structures. I don't see any other possibility. Next, we are going to show you resonance in benzene. The formula for benzene is C6H6. And it's a cyclic structure. Let me draw that. It's a double bond, single bond, double bond, single bond, double bond. So that's double bond, single bond, double bond in benzene ring. Now keep in mind, each corner represents a carbon. So this is carbon. Let's use a different color. Each corner represents a carbon, carbon, carbon. So that should be 6 carbon. Not only that, there is 1 hydrogen. Hydrogen. So altogether, there are 6 carbon and 6 hydrogen. Quite often we leave out hydrogens and we don't show carbon, just assume that each corner represents a carbon. Now then, how would I know how many hydrogens are bonded? Just simply knowing the fact that carbon must have 4 bonds. So that way you know exactly how many hydrogens are there. For example, in the bottom structure, I'm talking about the very bottom, this carbon has 3 bonds, 1, 2 for the double bond and third one. So obviously it must have 1 hydrogen. So that's how we find out how many hydrogens are bonded. Now, if this structure is given, can we find out what other resonance structure is possible? This is how we can do that. Try to bring this electron pair in between next carbon. Now I think for the time being, since you're learning for the first time, let's write down all the hydrogens. 1, 2, 3, 4, 5, 6. Now, in order to see another pathway for electron to go through, I need to play with these double bonds. Let's bring this double bond from its present location to in between adjacent carbon atoms. If that happens, then let me show you with red ink. This carbon that I'm showing with a red dot, big dot, would have 5 bonds. And that's not possible. What that means is the double bond that carbon has to move to the next location. So let's move it to the next location. And then temporarily this carbon would have 5 bonds. So that double bond has to break and move to the next location. And in other words, this would give rise to this structure, second structure. Draw it yourself, that we learn it better. So in other words, if one Lewis structure and is given to you, you can examine whether there is any resonance structure possible or not. And these are the 2 possible resonance structures. I'm writing down 1 and 2. Their combination would give a resonance hybrid, and textbooks often they write a circle indicating that double bond is not fixed or localized, it's moving around all the 6 atoms. Now we are going to talk about exceptions to the octet rule. Now there are 3 types of ions or molecules that do not follow octet rule. Ions are molecules with an odd number of electrons. Since octet means even number, so you cannot have octet with an odd number total valence electrons. Secondly, you may have insufficient number of electrons, so that you may not have octet. Or you may have ions or molecules with too many electrons, and in which case you'll have to break octet rule for the central atom. Usually it's the central atom for which you break the octet rule, not the outer atoms. In most cases, outer atoms maintain octet rule other than hydrogen. Hydrogen can only have 2 electrons. For example, NO here is shown with a dot on nitrogen. So you have an odd number of electrons. So either that electron, unpaired electron, is on nitrogen or it is on oxygen. So here you cannot have octet around each atom. Now you may have fewer than 8 electrons, like boron trifluoride. So boron trifluoride, if you write down Lewis structure of boron trifluoride, it's going to look like this. B, F, 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 and you give 8 electrons around. That's 24, and it doesn't have any more electrons. Now look at the central boron, which doesn't have 8 electrons. Now one can try to make 8 electrons by bringing electron pair from fluorine to boron, as you see in this structure. But that would give +1 on fluorine, which is highly electronegative, and -1 on boron. So here, this is an alternative way of explaining what we see in experiment, that all these BF bond lengths are equal or identical, and they are single bonded. So when you have a double bond, you see the formal charges are not very favorable. This fluorine gets +1, boron is -1. So highly electronegative element gets +1. So that's why this kind of structures are not very attractive. And so we say this is the best structure, boron trifluoride. So in other words, there'll be no double bond between boron and fluorine. Here we are showing you that BF3 with each boron fluorine having a single bond is the most dominant structure, because each fluorine and boron has 0 charge, and that's the most favored formal charge. Now look at here, 2, 4, 6, 7 assigned electron on fluorine and valence electron 7. So it's supposed to have 7, it does have 7. So formal charge is 0. In the same way, you can count formal charge for the other fluorine, which should also be 0. And boron is also 0 because it is supposed to have 3 valence electrons, and in this structure it does have 3 assigned electrons because there are 3 bonds and it gets one share of 1 electron from each bond. On the other hand, if you look at the other structures, double bonded fluorine has 2, 4, 6, and it's supposed to have 7 plus 1, plus 1, plus 1, plus 1. So those are less important. So most important is the far left structure. So basically you can say boron trifluoride has single bonded fluorine. Some cases, exception is pretty obvious, like PCl5. We know that we put at the center the least electronegative element or element present in least number. Phosphorus at the center, as soon as you put 5 chlorine or fluorine, it exceeds 8 electrons at the central atom. And that's why this is an exception, like PF5, PCl5, they all are like this. You have 5 atoms bonded and each has a pair of electrons, so basically you have 5 pairs of electrons around phosphorus. So it breaks octet rule.